All right, guys, hello. Sorry I'm not able to be there with you today. I totally forgot about this training that I have to be at, but hopefully these videos will help accomplish the same thing. Today we're going to be learning about NMR still, but this time it's going to be the high resolution NMR. What we were looking at before was just a standard NMR spectrum, and today we're looking at peaks that are better defined. So previously, we learned that peaks simply produce one single spike for different environments of hydrogen, and that peak will shift depending on what environment it was in. However, there is a little bit more information we can glean here. So what we didn't know is that these peaks actually form smaller groups of distinct peaks. Here in the picture, you can see on the left, we've got 4 small peaks all grouped together, which represent the CHO group. On the right, we've also got another group of peaks, but this time there's just 2 tall peaks. This is referred to as spin-spin coupling when we get this splitting of the peaks. And this splitting tells us quite a bit more about information about what is near the environment we are examining. So that's what we're going to take a look at. Now, in order to decipher these split peaks, we're going to be using the n+1 rule. Now, this rule is going to help us interpret how many hydrogens must be near the peak we see. So the way this works is you look at how many hydrogens are near the environment you're looking at. Not in the environment you're looking at, but next to it. So N refers to the number of hydrogens, and if you want to find out how many peaks your signal is going to produce, you count how many hydrogens are near your environment, and then you add 1. So for example, if you have an environment you're looking at that is next to a carbon that has no hydrogens at all, the value for hydrogens would be 0 plus 1. That means you're going to produce 1 peak. We would call that a singlet. Now, if you were examining a different environment that had a carbon next to it that only had 1 hydrogen, n+1 would produce a doublet. 2 peaks would be in that cluster. If you're next to a carbon that has 3 hydrogens, you get a triplet, again, n+1. If you're next to a carbon with 3 hydrogens, you get a quartet, and on and on and on. So the peak is always 1 more than the amount of hydrogens that are near it. Now, there are a few rules that go along with this about determining whether or not to count certain hydrogens. Firstly, hydrogens that are bonded to the same atom, the same environment that you're looking at, do not interact with one another. So for example, if you're examining a CH3 environment, don't consider the other hydrogens on that exact carbon. Okay? Only look to the carbon next to it to find the hydrogens that are nearby. Secondly, if there are hydrogens beyond the next door neighbor carbon, those hydrogens generally do not interact with the environment you're examining. So, for example, if you have 3 carbons and we're examining the environment here, the hydrogens that would be on this outer carbon would not affect this environment. The only ones that would are the ones that are directly adjacent. Okay. Next, if you have hydrogens attached to an oxygen that is directly adjacent to your environment, these are not going to show any splitting of your peak. So again, let me draw this real quick. if we are looking at the hydrogens here in this environment, and we've got, say, an alcohol group, this hydrogen would not register on the H NMR peak. We would consider this to be 0 hydrogens, and we would see a singlet here. Now, as before, as things get more complicated, the nature of the splitting also becomes more complicated. And so we're really just looking at the basics here. And so kind of keep that in mind, that things do get a little bit more complicated. They might not follow the rules quite exactly, but these are good rules to start things off. So let's go ahead and move on and look at an actual high-resolution graph. Here is the molecule ethyl ethanoate and its NMR spectrum. What you should notice right away by looking at this molecule here is firstly that there are 3 unique hydrogen environments, and we've labeled them. So we've got environment A, which is this CH3, and it's next to this ether group. We've got environment B, which is this CH2 group, and it's got 2 neighbors. It's got a CH3 and this ethyl group. Not ethyl, ether group, ester group, sorry, ester group. And then we've also got this third environment, C, a CH3 that's next to a CH2. Now, we can also deduce that there are 3 environments, not even looking at this structure, but just by looking at the spectrum, because we see 3 distinct signals on our NMR graph. Nextly, as we look at our NMR graph, you should be able to see that we've got some splitting going on. Now, if we look left to right, this first signal has 4 splits to it, 4 different peaks in this cluster. Then we've got a nice singlet here, and lastly, we've got a little triplet. That's going to be telling us information about what is, again, nearby, how many hydrogens are nearby. And we're going to be using the N+1 rule. So, if we look at A, we can see that near this environment, near A, we've really only got this ester here. And on this ester are no hydrogens at all. So N+1, 0 + 1 would mean 1. And therefore, it must be A that is producing this singlet here. Let's take a look at environment B. What is next to environment B? We've got the ester again with no hydrogens, but there is this nice little CH3 group, 3 hydrogens nearby. N+1 would be 4, so we got this quartet here. Now lastly is group C. In group C, all we have nearby is this little CH2. So N+1, 2 + 1 is 3, we get our triplet. So that's what's causing the triplet there. So this is just an example of how to look at a structure and look at the NMR graph and interpret information from it. Okay. All right, so now it's your turn. Here's a problem I want you to solve. Here I've given you the empirical formula, okay, and the high resolution H NMR graph. You can see that there is splitting at these different signals, and the integration traces are given for you. Firstly, what I'd like for you to do is determine the ratio of hydrogens in this compound. And again, you should reference that integration trace. Based on that, you should be able to determine how many total hydrogens there are and deduce the molecular formula. Once you have the molecular formula, please calculate the IHD for this compound and interpret what type of bonding must be present in the compound. Finally, look at those spin-spin couplings, the peaks that are being produced, to determine what types of hydrogen environments are probably present. Once you have done this, please draw the correct structure of the compound. You can use Table 27 to help you based on the shift data that you see in the H NMR. So, good luck. I will make a second video that talks you through how to solve this, but please work on this on your own first. Good luck.